According to the principles of quantum mechanics, the quantum state evolution process consists of two parts. Firstly, the linear evolution process. If a physical system is not measured, it will evolve in a deterministic and linear way according to the Schrödinger equation. Secondly, the nonlinear collapse process. If the system is measured, it will immediately and randomly collapse from the initial superposition state to one of the eigenstates of the observable being measured, in a nonlinear way. At this point, the experimenter will perceive a definite measurement value, namely the eigenvalue corresponding to the eigenstate. When measuring a quantum qubit, the only possible outcomes are that the quantum bit is in the state ket 0 with probability the square of the absolute value of alpha, or in the state ket 1 with probability the square of the absolute value of beta. The sum of the probabilities of all possible outcomes is 1. There are many ways to perform quantum measurements, such as projective measurements, positive operator-valued measure. When we measure a physical property of a system, such as its momentum or position, we need to specify a real number. Each possible measurement outcome corresponds to an eigenvalue, which is described by the projection onto the eigenspace corresponding to the eigenvalue of the observable. Since the vector is normalized, the state after measurement can be described by the eigenvalue and eigenvector. In quantum mechanics, measurement leads to collapse, which means that measurement affects the original quantum state. So far, we cannot directly store and read information on quantum states. We can only collapse them onto classical bits to obtain the probability distribution information obtained by measurement and approximate the true quantum state information. Of course, this process requires a large number of measurements to obtain the probability distribution.